Good morning. Maki Manchola, the speaker. I'd like to thank Florida International University for their assistance with this presentation. Okay, this is the first of a small collection of lectures on topics of differential equations I want to put together. And this one in particular deals with the method of variation of parameters. Okay, together with this lecture, there is some reading material, which you occasionally see on the screen. So I might refer to it when I see that writing on the board will be too time-consuming. So first, let me sort of introduce the basic problem that we want to look at and then view it in a more general context. For example, let me show here the type of equation that we will solve using variation of parameters. The second order linear differential equation of the form y double prime plus bx, here a function of x, suitable, of course, plus c of x, y, equals to some function which we will require to be suitable for whatever computations we make today. Now, the way we're going to approach this here is we're going to transform this equation into a matrix, a linear equation by making a substitution. Here is the first substitution we're going to make. Let z be the first derivative of y. So what we get here is then z prime is the second derivative of y. Now, doing this as a system of linear equations, we have z prime right here. I'm going back to the original equation here, c prime, plus b, I'm going to drop the reference to x, although we understand there is one, y prime, which we are naming z, plus c y equals f, and of course, the substitution we made. So the system we have now, we have transformed the second order linear equation into a system of equations which is as follows. Z prime equals to negative cy, when we send that one to the other side of the equation, minus bz plus f. That's one of the equations. The other equation, of course, is y prime equals z. I will put this one at the top. Y prime equals z. There we have it. Now we can write this one, of course, as a matrix linear equation, matrix linear binary differential equation, as a y z prime, we understand this means y prime z prime, equals 2. Now we're going to create a matrix here. As follows. This one has 0 y plus 1 z. The second one has negative cy minus bz. So you can see, multiplying the first row here with this matrix will produce z, and here the second row will produce this part of the second equation, and then the f, we're detaching it just so that it has the proper form, which is of the form a vector prime equals a y plus b. This is a linear, we know it to be a linear equation. Now, so how are we going to solve this equation right here? The basic idea here is to solve the matrix equation via what we're going to call variation of parameters. Now let's assume in general, now we're going to study this in general. Let's assume general. Let's start with a fundamental matrix solution. Fundamental to the corresponding homogeneous equation to this one right here, which is y prime equals ay. Now let's recall that these are now vectors. In our particular example right here, that vector was a dimension 2, but it could be any dimension, as when we treat this problem here. Now, what is a fundamental matrix solution? Well, we understand that such is a fundamental matrix solution. Such is a matrix that contains all possible solutions to this. Our reference, Wolfgang and Walter Wolfgang, has some facts about it. It says that an nth order differential equation, an nth order differential linear system will have n linearly independent solutions, which we'll put in this fundamental matrix. So let's start with this. Then we would like to make an educated guess here about what would be a solution to the non-homogeneous system. This is, as you may recall, this is known as a non-homogeneous system. Well, this one is homogeneous. We can always get a solution to a homogeneous system quite readily. Now, so what about the non-homogeneous system? Let's say, suppose that there is a solution U of the form of the form Y times Z, where Z here is a non-constant, where Z here may not be a constant matrix. Now, what we get is that we would like to solve for Z if that's possible. So let's see. Let's assume that this is a solution to the non-homogeneous equation. Then let's say attempt to find Z here. Whoops. So here we go. We're going to apply here the product rule. Y prime will be, U prime will be the derivative of the first times the second, plus the first times the derivative of the second. Now we plug this into the equation. We're going to apply this into the original equation. So let me just set up a nice array here. We know U equals YZ. I want to plug it in here, where I'm assuming U is a solution. So I want to get A here. Now, I'm going to pretend I send this to the side. So this is going to actually be negative. Now, since we're assuming U solves this equation here, then what happens when we combine these two, we're going to get B. Now, since we know Y is a fundamental solution, then right here we're going to get, on the right-hand side, something that's going to become 0. So this is a Y prime minus a Y factor of the Z plus YZ prime. This is right here 0 because we know this solves the homogeneous system. So when we bring this to the left hand side, you get 0. So here we have found the following. We have found the way of relating Z prime with B and Y. That is Z prime equals the inverse of Y times B. Now recall this is a matrix, of course. So if we wanted to solve for Z, we will apply formal integration here, of course. And the reason I say formal is because we're just manipulating symbols here. It is, of course, it is known from our references that such things can be done. All right, so that is essentially the method of variation of parameters. Very short method, very easy to come up with, and it's very useful when we're solving this problem right here. How is it useful? Well, just recall that we are able to transform any second order linear differential equation into a linear system, linear non-homogeneous system. So when we approach solving this system, we just find the fundamental matrix solution and then proceed to find the solution or a solution to the non-homogeneous system by applying the method of variation of parameters. Now, I'd like to exemplify the method itself. So I came up with an example, which I will show here in the camera, document camera. All right, so I'm asking to solve a non-homogeneous system. So here is the example. Now I would like to write a little bit of it on the board so that you can see it. And then when the detailed time comes, I will refer back to the document camera. Let me first clean this up here, please. All right, so the example is let's solve the following linear homogeneous system. It's a 2 by 2. Look at it for a minute. All right. 1, 1. -2, -1. Now this will be y, of course, which I'm going to call y1, y2, plus a b. In this case, my b, I decided to use this nice little nonlinear term. Right here. All right, so first thing we need to do is get this homogeneous system solved. In other words, we need to find the fundamental matrix solution for this one. All right, so here is we could do this two ways or more. One way uses rather sophisticated tools of systems of linear differential equations. That means we use the exponential matrix. We involve an exponential of a matrix in it. For this occasion, I'll just do it in a very rather elementary manner. In other words, I'm going to just set up a couple of equations here for y1, y2. I'm translating this into equations right now. Now, when I do the multiplication here, in the first row, I get y1 plus y2. When I do the second row, carry out the multiplication, I'm going to get negative 2 y1 minus y2. This may not be a very usual way of solving problems like this, but let's do it today. It's a nice, sort of a nice calculus differential equations type of problem, basic one. All right, so how we're going to solve this system, the idea here is to make some substitution. So let's do the following. I have a system of equations and I would like to sort of eliminate some stuff here. So I see here that I can get y2 explicitly in terms of y1. y2 equals to y1 prime minus y1. I can use this to get the derivative of y2. Notice that this is a plain formal manipulation. If we were solving this problem, we'll need to sort of have that this y1 prime is actually differentiable. So I just differentiate y2 by taking the derivative of the right hand side. Now, what I'm going to do now is I'm going to make some substitution now on the second equation. So let's do that right here. We get to substitute y2 prime by y1 prime minus y1 prime. That substitutes y2 prime equals to negative 2y1. That's out of the second equation. Minus, I seem to have made an error here. Please point back to this first board. I enter 1 instead of a 2. My apologies. Now, in reading here y2 properly, now I can just go back here and make the substitution. Minus y2, which we know from our solving the first equation is y1 prime, the first derivative of y1, minus y1 itself. Now notice that in this substitution now we have obtained a second order linear equation, and in fact this one will be a homogeneous one. We have methods, basic methods to solve this one from basic ordinary differential equations. So let me just point you to the document camera to outline the solution of that. So I'm pointing right now at what I have on the board. After we simplify, we get the second order equation, y1 prime, in other words, the second derivative of y1 plus y1 equals 0. We will use an auxiliary equation. The auxiliary equation is r squared plus 1. Such yields r equals I or negative I. When that happens, we know how to solve this to get two linearly independent solutions to this second order equation. One of those is cosine of x, the other solution is sine of x. So let me go back to the board right now to record that. So we obtain here two linearly independent solutions. Yes, cosine cosine of x and sine of x are linearly independent. It's simple to show. Now I'm putting subscripts to y1 because we're solving the equation here for y1. But since it gives me two linearly independent solutions, then I'm going to call one the first one, and I'm going to call the other one the second one. Now, so we now need to proceed to get the y2. Remember that this is a system of equations that involves the y1, and going back in here to the original problem, it also involves the y2. We need to find out what that is. So we just go back to the substitution we made here, which is y2. y2 is equal to y1 prime minus y1, but we have two linearly independent solutions. So we're going to use one to get a y2, and then we're going to use the other one to get another y2. We later will see that what we get allows us to form a fundamental matrix solution to the homogeneous problem we're trying to solve right now. So let me call the first one, let me use this first. So I'm going to call this first y2 is equal to the derivative of y1, 1, minus y1, 1 itself. We know the derivative of cosine of x is simply a negative sine of x, minus y1, 1, which we have is cosine of x. All right, so here's y2, 1. Let's get y2, 2. y2, 2 is y1, 2, right? Because now we are using the second solution, prime minus y1, 2 equals. Now, find the derivative of sine gives you cosine of x minus sine of x itself. Now, what we have obtained so far is a pair of solutions. One of them is y11, y21, it's a column, and y12, y22. Now going back to the document camera, I have recorded this in here, so I'll just sort of point out what we did on the board. Now there is a little issue of whether these two vectors that we have obtained, namely the first vector y1 and y21 and y12, y22, whether they're linearly independent. If you look in here, there is a sort of small argument of that. I'm going to take this off. This will be put on the reference material, so this won't be gone forever. It will be available with the lecture. So the claim here is that if we form the matrix Y, first column, the first solution we obtain, second column, the second solution we obtain, that's a fundamental matrix. This will have to be checked. Now once it is checked, then we now are done solving the homogeneous system. So let me now point out what's next here on the board. I'm going to erase a little bit here. Whenever we need reference, just go back to the document camera. All right, so what do we have so far? We found a fundamental matrix. Fundamental matrix solution for or of this homogeneous equation. Oopsie. So So now what we need to do is apply the method of variation of parameters to solve the given non-homogeneous problem, and of course that entails computing the integral of what? The inverse of the fundamental matrix solution multiplied with -1 tangent x. Computing the inverse is a little bit time consuming. This is as we know, it's a linear algebra problem. So what I will do is I will make a reference here to some supplemental material I will have. Please, let's look at the document camera for a minute. This is a linear algebra problem, computing the inverse of a matrix. So I'm doing this in general here. When I have a matrix and I compute its inverse, here's what we get. Now I'll just translate this into the problem that we have at hand, which is computing the inverse of the fundamental matrix. Computing the inverse of the fundamental matrix in this case yields this one right here. Y inverse, the inverse of the fundamental matrix system, is this expression here, this matrix expression right here. Now, one question that becomes of importance here is whether this exists. For this particular example, we're going to limit for the moment being, in fact for this whole lecture, we'll just limit ourselves to the exercise that we have at hand. Yes, this one is invertible because there is no undefined parts when you compute the inverse, the formal inverse. The references that I'm presenting at the end of the reference material, the reading material, will point to sources that actually establish that in general the fundamental matrix is invertible because we know those columns in it are linearly independent. Alright, so here we have, after computing the inverse, we get this nice little matrix. So I'm going back to the board right now. So we find, let me retrieve this for a minute here. We have find, after some work, we find the inverse of the fundamental matrix for this example. I have found it to be a couple of times, so I believe this is correct. Cosine of x minus sine of x minus sine of x, sine x plus cosine x, and then cosine x. So that's what I found it to be. So now I can get this here, which is going to be the part that we're missing in our problem. In other words, this will be our z. Making reference to my earlier writings on the board. So I'm going to finish computing z here. In the second board, z equals to the integral of the inverse of y, which is cosine x minus sine x, sine x plus cosine x, and then negative sine x, cosine x, multiplied by negative 1 tangent x, the vector or 2 by 1 matrix. Alright, so what we get here, if we point back to the document camera, it's a rather meticulous computation to do. Some integration problem in computing each of the individual integrals. One of the integrals that we obtain here is a sine of x minus secant of x. When we perform the integral of secant of x, you know, this is one of those tricky integrals where we had to multiply the top and the bottom by secant of x plus tangent of x. Upon doing that, we get the integral of secant of x to be the natural logarithm of secant of x plus tangent of x. Now in the integration here, we get some constants. We can always set them to any value we want. They're arbitrary. They're for this particular example, I'm just being lazy and putting 0 for them. So there is our z. Let me make a correction in my page here. This is what I called earlier z. So that will pretty much solve this. Oops, excuse me. This pretty much solves the problem, because now we have the solution to we have the solution we're looking for, which was u equals to y times z. We found z just now to be, let me catch the paper here, going back to the board. So we found u equals yz, y times this nice little matrix here, negative cosine of x. Excuse me, let me copy it from my paper. I have gotten on my paper that this was the matrix negative of cosine of x plus the natural logarithm, that's the value of secant of x plus tangent of x, and the bottom was sine x. Now we already know what y is, so this will be rather, I'll put the negative in front. This will, of course, will be a rather laborious computation, so I'm just going to leave it in this form. Sine of x. And now what y was, let me see, was cosine. Cosine of x, negative cosine of x, minus sine x. I hope I'm not mistaken. If I am, I'll just make a little correction in a minute. I'm working here by memory. I believe this is sine of x minus cosine of x. Okay, so let me confirm this at this moment. Okay, so this is this is incorrect. It was cosine of x minus sine of x. Okay. So there is the example. We're done solving this matrix linear equation. Now, so there is an example in the method of variation of parameters. In the reading material, you will find the reading material, which will be accompanying this lecture. You'll find the details of the method itself and how to actually apply it to our original question. I'm looking here at the second order linear ordinary differential equation. And here we will see the transformation in detail in the reading material. Let me scroll down page by page here. We can extend that method of converting a second ordinary linear ordinary differential equation to also a third order equation, or a fourth, or a fifth, an nth order linear differential equation. The reference is made at the end of the reading material to a textbook that actually identifies the problem in general. The method is the same. Now, so here's the transformation. Here are the details of the transformation. Some exercises come with the reading material. Some solutions will be posted after some time for the reading material. And here are some details about why the method works. In other words, we always have the method work because in solving the linear equation, it is in solving the matrix linear equation, you make reference to the original second order differential equation. Now, so going to the last page here, there are quite a few details here to be read. I have expanded on them as much as possible. When at the end, you will find the references that serve to accompany this lecture and reading material. One of them is by Walter Wolfgang, and the last one is by Lawrence Perko. Thank you very much. I have completed this small lecture.